Ever wonder how AI knows when it's seeing something completely new? Like what if a self-driving car encounters a spaceship? Or a medical AI analyzes a scan that doesn't match anything in its training data? That's where out-of-distribution, OOD, detection comes in, a crucial tool for helping AI systems recognize when they're dealing with the unknown. Today, we're breaking down a groundbreaking approach called PRISM, which is changing how we teach AI to know what it doesn't know. Let's start with the basics. Most AI models are super good at recognizing patterns they've seen before. But they're not perfect. Imagine a neural network trained to identify cats and dogs. If it sees a raccoon, it might guess cat or dog with high confidence, even though it's never seen a raccoon. That's a problem. We need systems that can say, wait, this isn't part of my training data. Traditional methods try to spot these out-of-distribution samples by looking at confidence scores or probabilities. But here's the catch. They often rely on strict assumptions about the data, which don't always hold up in the real world. That's where PRISM steps in. So how does PRISM work? Instead of just looking at final predictions, it digs into the model's intermediate steps, like the thought process before the final answer. It uses something called pseudo-labels, which are smart guesses about what the model should be seeing. These pseudo-labels help the system create a hidden map of what normal data looks like. Here's the magic. When the model encounters something unfamiliar, it doesn't fit on this map. It's like a GPS that suddenly shows a landmark off the route. PRISM measures how far new data is from this map, flagging anything that strays too far as OOD. But how does it learn this map? The researchers designed a simple yet powerful rule. They combined two goals. 1. Accuracy, train the model to recognize known data, like cats and dogs. 2. Subspace distance, push unknown data like raccoons away from the map. This dual approach helps the model not only classify familiar data well, but also spot surprises more effectively. In experiments, PRISM outperformed existing methods on real-world datasets like CIFAR-10 and CIFAR-100. And the best part? It doesn't require massive computational power, making it practical for real-world applications. So why does this matter? As AI powers critical systems, medical diagnostics, autonomous vehicles, even climate models, we need models that can admit uncertainty. PRISM isn't just a technical win. It's a step towards safer, more reliable AI that can handle the unexpected. Now, let's dive deeper into what makes PRISM so effective. Imagine training a robot to spot fake paintings. You don't just want it to catch obvious fakes, it needs to avoid screaming bam. Fraud every time someone paints a sunset. That's where two key metrics come in: false positive rate FPR and AUROC. FPR is like the robot's panic level, how often it falsely flags normal stuff as suspicious. Lower FPR means fewer false alarms, right? Now, AUROC measures how well the model distinguishes between normal and weird data. Think of it as a radar screen. The higher the AUROC, the clearer the separation between safe and suspicious signals. In the study, PRISM smashed the competition. On the LSUN dataset, it had an FPR of just 6.71% compared to SNN's 7.71%. That might sound tiny, but in AI terms, it's like cutting down on unnecessary alerts without missing the real threats. And here's the kicker: PRISM didn't just excel at spotting anomalies. It also maintained top-tier ID accuracy, meaning it still nailed recognizing the everyday stuff it was trained on. Visuals back this up. Picture a histogram where PRISM's confidence scores for normal data cluster neatly on one side and strange data huddle on the other, like two distinct groups on a radar. Or a confusion matrix showing PRISM's clean, focused predictions. This isn't just about being clever in the lab. It's about building AI that's reliable in the real world. So why does this matter? Lower false alarms mean less wasted time, and better accuracy means smarter systems. PRISM's results suggest we're one step closer to AI that's both cautious and confident, perfect for applications from medical diagnostics to cybersecurity. Next time you see an AI make a mistake, remember, researchers are hard at work helping it say, I don't know, and that's a game changer.